Welcome back, mathematicians. We've moved on to section 3.5, derivative of trig functions. That should be derivatives of trig functions. So, first we're going to start off by the proof of the derivative of sine of x, and then all the other ones I'm going to kind of explain what the proof is behind it and the reasoning behind how we get that derivative. So first, let's let f of x equal sine of x, right? We know that f prime of x is going to be the limit as h goes to 0 of sine of x plus h minus sine of x divided by h. Now remember what we learned in chapter 1, that sine of a plus b is going to equal sine of a cosine of b plus cosine of a sine of b. So we can use that to rewrite this limit as h goes to 0. So instead of sine of x plus h, we'll have sine of x cosine of h plus cosine of x sine of h minus sine of x all over h, right? So now what we're going to do is I'm going to pull out a sign in this term and this term, every term that has a sine of x. I'm going to collect all of them. So that means I'm going to have sine of x times cosine of h minus 1, because if I pull out a sine of x out of minus sine of x, that's just going to leave me with minus 1, plus cosine of x sine of h. Still everything's over h. Now, if I have some fractions, I have something plus something over one number. So I can write a plus b over c as a over c plus b over c. I'm basically just splitting up one fraction and making it 2, just so I can then distribute this limit, because limit laws say that I can add the limits of the two functions added together. So that means I'm going to have sine of x cosine of h minus 1 all over h plus the limit as h goes to 0 of cosine of x sine of h over h. Okay? So I kind of did 2 steps in once, where I split this one big fraction into 2 fractions, and then I also distributed the limit. Well, I know that sine of x has nothing to do with as h goes to 0. So I can pull that out front of the limit. So then I'm just worrying about the limit as h goes to 0 of cosine of h minus 1 over h plus, again, cosine of x has nothing to do as h goes to 0. It's almost technically a constant with respect to h. So I have cosine of x times the limit as h goes to 0 of sine of h over h. Now what we've seen in past lectures is that the limit as h goes to 0 of cosine of h minus 1 over h, we know that that is going to go towards 0. And the limit as h goes to 0 of sine of h over h, we know that that's going to go over 1. So putting those all together, we'll get sine of x times 0 plus cosine of x times 1. Simplifying once again, and we just have cosine. So if you're keeping track of all the derivative rules that we know so far, this should be like number 8. And so we can say that the derivative with respect to x of sine of x is cosine of x. We can do the same proof for cosine, but first let's do some few examples. Oh, I'm about to sneeze. Okay, so we're gonna find y prime when y equals e to the x times sine of x. Ooh, bless me, sorry. So this is product rule. I have a function of x and times another function of x, okay? So sometimes I like to kind of make a toolbox of all the derivative rules I'm going to use. So I'm going to use product rule. I'm going to use the derivative of sine of x, and I'm going to use the derivative of e to the x. Those are all special derivative rules. So y prime is going to equal e to the x's derivative times sine of x plus e to the x times sine of x's derivative. That's what I mean when I put that little prime right there. Just another way to write it. E to the x's derivative, I know is just e to the x. So I have e to the x times sine of x is my first term, plus e to the x times, I now know that sine of x's derivative is cosine of x. And we're done. Just like that. Alrighty, so our ninth derivative rule is that the derivative with respect to x of cosine is negative sine of x. And you can show a similar proof of this using the same way we did here. Obviously, not using sine of x plus h, you use cosine of x plus h, and you would use a different rule. So let's do another example. And we're going to find y prime when y equals cosine of x times sine of x. So I'm looking around my toolbox. What am I going to use? I have a function of x times another function of x, aka a function of x as I'm putting x in and getting something back out. So that means I'm going to use product rule. And sine of x, and then my newest derivative rule, cosine of x. So y prime is going to equal cosine of x's derivative times sine of x plus, I'm going to keep cosine of x and now take the derivative of sine of x. So cosine derivative is negative sine of x times sine of x plus cosine of x times cosine of x. And I can simplify that to give me negative sine of x squared plus cosine of x squared. We write this little squared right in front of sine, kind of just like how we do this similar for logs. So when I say cosine squared x, that equals like cosine of x squared. It does not equal cosine x squared. Two different things. Okay? Just want to clear that up if anyone was confused. So I want you guys to notice something really interesting. So if f of x equals sine of x, f prime, the first derivative is going to equal cosine of x. I just learned cosine of x's derivative, making f double prime of x negative sine of x. Well, then f triple prime of x is going to equal the negative derivative of sine of x, So that's a negative cosine of x. So then f to the fourth is going to be negative sine of x. Well, that's just sine of x, and I'm back to where I kind of started, and so on, and this would keep going. So like f to the fifth, we get cosine of x, and so on. So it kind of has this loop of the four of them: sine, cosine, negative cosine. Alrighty, and that's the little chain. Alrighty, so then rules 10 through 14. No, 10 to 13. So we're going to have the derivative with respect to x of tangent of x is also the derivative of, remember how we can rewrite tangent of x as sine over cosine, sine of x over cosine of x? That's going to give me secant squared x. If you ever forget tangent's derivative, but you remember sine and cosines, well, that's sine divided by cosine. I can use quotient rule and those two derivatives to get its derivative. I then will need to simplify a little bit to pull out secant squared. So then the derivative with respect to x of cotangent of x is the same as the derivative with respect to x of, remember, cotangent is just 1 over tangent, or cosine of x divided by sine of x. It's good to know these just in case you forget the derivative of cotangent. You can derive it really fast. And that's going to be negative cosecant squared x. The derivative with respect to x of secant of x is the same as the derivative of what? Whenever cosine of x, good job. And that's going to give you secant x, tan x. The derivative of cosecant x is going to be the derivative with respect to x of 1, oops, I don't like that parentheses, 1 over sine of x. And that derivative is, if you've seen the pattern so far, it is negative cosecant, actually no, it's positive, cosecant of x, cotangent of x. Just kidding, I'm going to check that really fast. Ha, it is negative. I was right. It's like that pattern doesn't work. Notice that every co-whatever derivative is going to be negative. So cosine's derivative is negative sine. Cotangent's derivative is negative cosecant. Cosecant's derivative is negative cosecant x, cotangent x. So that's a good way to remember it. Alrighty. So let's do a few examples because there's lots of different ways to, since we can simplify 4 of these trig functions into sine and cosines, sometimes one answer might look very different than another, but they're the same answer. So for 3.5.13, we're asked to find dy dx, the derivative of y with respect to x. So we're given that y equals 4 divided by cosine x plus 1 over tangent of x. So we're going to do it one way, and we'll choose some cute colors. So this way we'll do it in blue. Does that look nice? Yes, I agree. Okay, so then I would rewrite this as y equal to 4 secant of x plus cotangent of x. That's how I want to rewrite it. Because I just have these really quick rules. And if I see something divided by something else, then that screams quotient rule. And that formula isn't my favorite, just saying. I know I shouldn't play favorites, but it's not my favorite. So I've just rewritten y right now. So now I can take the derivative y prime, and that's going to give me 4 times the derivative of secant plus the derivative of cotangent. Since we just learned those, I can go grab them really quickly. So that's going to be 4 secant of x tangent of x minus cosecant of x cotangent of x. I don't really think I can simplify that much at all, so we're just going to leave it there. So another way we could have done it is just left y as 4 over cosine of x plus 1 over tangent of x and done quotient rule. I don't suggest doing quotient rule when you just have a number in the numerator, because you can easily make whatever in the denominator something to a negative power. So, and then it's just like 4 times something to the negative power. In this case, cosine to the negative power is secant. So that's my recommendation. Just because a lot of errors can come out of using quotient rule if you forget how to use that rule. And power rule, I think, is a lot easier to use than quotient rule. That's just my opinion. That might be a hot take. I don't know. So if we do quotient rule, we're going to have to do it twice. Again, see, not very fun. So quotient rule is low d high, the derivative of 4 is 0, minus high d low, all over low squared. Right, so that's how I got cosine times 0. That's d high, the derivative of just 4 is 0, minus 4 times the derivative of cosine, which is negative sine of x, all over cosine squared. Now let's do it again for 1 over tangent of x. So I'll get low, which is tangent in this case, times d high, 0, minus high, which is 1, and then d low. Tangents is secant squared, ooh, I almost wrote theta, x, over tangent squared x. I keep writing theta. 0 reminded me of a theta. Okay, this, I need to do some simplification. So cosine times 0, that's 0. So negative 4 times negative sine. So it's going to give me 4 sine of x divided by cosine squared x plus tangent times 0 is 0. So just negative secant squared x over tangent of x. Also, I just realized cotangent's derivative is not cosecant cotangent. What am I thinking? If someone caught that earlier, good job. Negative cosecant squared. It was literally right there. Sorry, brain fart. Okay, cool. So then sine over cosine is going to be, sine over cosine squared. That's going to be sine over cosine times 1 over cosine, which is the same as secant x tangent x, minus secant squared over tangent squared gives me cosecant squared. And that's how I get the same place. You could have stopped here, totally been fine. Could have kept going on here. And you can see it's kind of whatever your preference is. If you just absolutely love quotient rule, please go on and use it. Love quotient rule. It needs some love. If you love knowing all the trig rules and not messing them up like I did, then I would rewrite it just to make your life a little bit easier. Alrighty, so let's do one more example. This is 3.5.26, one of my favorite problems. So now we're asked to find dr d theta, which is probably why I was using thetas last time. So r equals 1 plus secant theta times sine of theta. So I have a function times another function, product rule. So what I kind of want to first do is kind of what we did before and simplify. So I can make r equal to, I can distribute out and I'll get sine of theta plus, remember secant theta is just 1 over cosine of theta times sine of theta, which is just sine theta plus tangent of theta. Well, I know I can take that derivative really easily. Sine's derivative is cosine of theta, and tangent's derivative is secant squared of theta. Beautiful. But what if I just don't think it would do that? I just see two things multiplied by each other. I can't remember what secant is right now, but I know it's derivative. Let's just keep rolling. So then we can just leave r as 1 plus secant theta. And use product rule. Nothing wrong with that. So then r prime, I'm going to take the derivative of secant theta, or sorry, 1 plus secant theta. So the ones is going to be 0. And then secant theta's derivative is secant theta tan theta times, I'm going to leave sine theta all alone, it's not his turn yet, plus, I'm going to keep 1 plus secant theta times the derivative of sine theta, which is cosine of theta. Running out of space. There we go. Now I can simplify. So now I have secant theta, tan theta, sine theta, plus, distribute this cosine theta plus secant theta, cosine of theta. Well, this just looks like an absolute mess. So let's simplify. Remember, secant is 1 over cosine, so secant theta times sine theta is going to give me tangent theta, so this is going to be tangent squared theta plus cosine of theta. Secant theta is just 1 over cosine, so secant times cosine is 1. Well, how do I had secant squared. How do I have what? I have plus 1 and I have tangent. Ooh, what is going on? You need to remember that one of our trig functions is that secant theta equals tan theta squared plus 1. So then we can get back to, if you wanted to, this is a perfectly beautiful answer as well, but it's how we can get back to secant squared theta plus cosine of theta. Just kind of showing you that these two answers are the same. So I'm pretty sure putting these answers into my math lab should accept both. If they don't, email me, we'll figure something out. So that's how these two ways of doing a problem in blue and a problem in pink can get us to two different spots, but they're actually the same. So it's up to you how you want to do it, but with a lot of these, you can think smarter, not harder. You're still thinking harder in my opinion, so I don't like that phrase, but I would maybe try to simplify an expression first and then take the derivative because it might help you out in the end. Okay? So that's all for this one. This is pretty short as well. You guys have a test tomorrow if you're watching this on Wednesday, as you should be. So good luck on your test tomorrow. Bailey should have already posted a review for you. And I will see you guys after Memorial Day on that Tuesday.